Hello everyone, I am Aishwarya, PA of course CS253. Today we will be talking about NumPy. NumPy. NumPy stands for Numerical Python. It is an open source Python library for scientific and numerical computing. It uses multidimensional arrays as a data structure and provides fast and efficient processing of the same. NumPy has been used extensively in many data science and scientific Python packages like Pandas, SciPy, Matplotlib, and so on. To install NumPy, the users need to run a single line command depending on the environment in which they want to install. If you're installing it in Anaconda, running the command conda install NumPy will install NumPy in the environment. And similarly, pip users can run the command pip install NumPy to install it. Multidimensional array object. NumPy uses multidimensional arrays as the data structure. An array is defined as a grid of homogeneous elements which can be indexed in various ways. By homogeneous elements, we mean that all the elements present in an array should be of the same data type. This is different from Python list, which can store elements of different data types. So in a list, it is possible to store the integers, floats, a string, and so on. But in case of array, all the elements should be of single data type. Like an array can be store multiple integers, or array can store multiple floats, but it cannot happen that the same array is holding integers and floats in NumPy. Now NumPy implements these multidimensional arrays as an instance of a class ND array defined in NumPy. How to create an array in NumPy? So there are mainly two ways to create NumPy arrays. The first is that we can use the list in Python. Note that the list should be of homogeneous elements. And the second option is to use NumPy functions like zeros, ones, empty, arrange, linspace, and so on. Let's look at these functions one by one using code. So in this code, we have imported NumPy as NP. Now, in line 4, I define A as a list of integer values. To create a NumPy array using this list, we will be passing the list A as an argument to the function np.array. So any list which is being passed as an argument to the function np.array will result in a NumPy array. This list was a list of elements. It has resulted in a one-dimensional array, which has been printed here. What if list is itself what if the elements of a list is itself a list? So in line 7, we have defined B as a list of list, which means that the elements of B itself is a list. Note that all the elements in B have the same length, and all the list elements of B are holding the elements of the same data type. Here it is integer. Now, if we pass B as an argument to the NumPy array function, so np.array of B, it will result in a two-dimensional array, which has been printed here. Okay, so this is how we can create a function. We can create an array using a function np.array by passing an argument, which is a list. The second option is that what if we do not have these elements or the list from which we want to create an array, but we know the shape of an array. So let's say we want to create an array of shape 3, 4. That means it will be having 3 rows and 4 columns. And now we want to create a NumPy array with this shape. So there are multiple factors. The first is this np.empty, which will create an array with the same shape, which will be passed as an argument to it. So this will result in an array of size 3, 4, which has been printed here. Similarly, we can use np.zeros, This will also create an array with the same shape, which is 3, 4. Note, since it is np.zeros, all the elements will be initialized to a value of 0. In case of np.ones, the array will be created with the shape 3, 4, but the elements will be initialized to the value 1. Apart from these, there are two other functions which can help in creating new arrays, and they basically create an array which is initialized with a sequence. So for this, we use the function np.arange. This function is very similar to the Python's function range. It uses 3 arguments: the first number of the sequence, the last number to stop generating the elements of that sequence, and the third argument is the interval size of the sequence. So by running this command np.arange 0, 100, 10, it will generate sequences from starting from 0 up till 90 with an interval of 10, and this will result in a one-dimensional array. Similarly, if we use this function np.linspace, it will generate the specified number of elements in the interval. So it again takes 3 arguments. The first number is the starting of the interval. The second number, the second argument is the ending of the interval, and the third argument will be the number of elements which should be generated in this interval and should be equally spaced. So by running the command np.linspace 0, 90, 10, it will result in a one-dimensional np.array with elements starting from 0 up till 90, because it's inclusive, and at an interval of 10. Okay, so once we have created these arrays in NumPy, we would like to do certain operations on it. So it's very easy to perform any operation on these arrays. The algebraic operations performed on arrays are very similar to performing algebraic operations on simple elements like integer values or float values. Here, the only difference will be that it will be done on element wise. So what I mean, so let's see it by an example. A is an array which we have created using Python list, passed as argument to the function np.array. B is another NumPy array which has been created by using another list passed as an argument to the function np.array. So here A and B have been printed, and now we will try to perform some algebraic operations between A and B. So using an operator plus, we can just do this A plus B, and this will result in a new array with each element being so it's like element wise addition of this array and B. So the first element of array A will be added to the first element of array B, resulting in the first element of the new array A plus B. So 6 plus 16 will result in 22, and so on. Similarly, for subtraction, we use the operator minus, multiplication, asterisk, and division slash. All these operations will be performed element wise. The second kind of operations which we generally want to perform is these logical operations. To perform logical operations, NumPy provides certain functions. So this logical AND will do the logical AND operation between these array and B. So note, in Python, anything which is not 0 is termed as true. Since this array has no element marked as 0, it will be evaluated true. Similarly, array B will be evaluated true at all the places, and their AND should also be true. So this can be seen here. So here there is a logical AND evaluation true. And similarly, for logical OR, it will also evaluate true. The other common operations performed on array is finding the sum of the array and the minimum and maximum element. The sum of the array can be found along any axis, as well as it can be found for the entire array. And similarly, for other operations like reversing an array or finding the minimum and maximum. Now we can find the sum of an array using the function np.sum, which takes two arguments. The first argument is the array, and the second argument is the axis along which we want to find the sum. So if we can look at here by an example, so this is our array A for which you want to compute the sum. So if you want to perform the sum of the array along axis 0, it means we are doing the column by sum. So it will be -4 plus 9 plus 1, resulting in 6. Similarly, the sum of the second column, 6 plus 3 plus 8, which is 17, will be written as the second element of the array. Now, if we perform the sum of the array along axis equal to 1, this will result in a row-wise sum of the array, which will be -4 plus 6 plus 8, resulting in a 10. Similarly, the second row sum will be 13, which is stored here as the second element of the array. The other frequently used operation is reversing an array. Again, we can reverse an array using a predefined, using a function which is already provided in NumPy called np.flip. It also takes two arguments, the array itself and the axis along which you want to flip. So in case we do not mention any axis, then the entire array will be completely flipped. So if you see here, the zeroth, so the element -4, which was present in the 0th row and 0th column, has now become the last element of this 2D array. The next element 6 has become the second last element of this array. So if we have, if the axis argument is not provided, then this is how the array will be reversed. If you want to reverse an array specifically along axis equal to 0, then all the columns individually will be reversed. So -4, 9, 1, that is the first column, will now become as 1, 9, -4. The second column, 6, 3, 8, will become 8, 3, 6, and so on. Similarly, if we reverse an array along axis 1, it will result in all the rows reversed individually. So -4, 6, 8 will now be changed to 8, 6, -4. 9, 3, 1 will be changed to 1, 3, 9, and so on. The other operations which are usually performed is sorting an array and joining multiple arrays. So if you want to sort an array, we use the function np.sort and np.argsort. So again, A and B are the same arrays which we have defined above. And let's perform the sorting operation on the array A. So this is the array A, which is unsorted. Now, when we try to sort an array, if we do not mention any axis, then this 2D array will be first converted into one-dimensional array, and then it will be sorted. So this is how it will return if axis is none. So that means all the ones first, then 3, 4, 5, 6, 8, and 9. If the axis argument is specified here, so axis equal to 0 means sort the columns individually. So now these columns will be sorted. So it will be 1, 4, 9, 3, 6, 8, 1, 5, 8. Similarly, if the argument axis is given a value 1, then the rows will be sorted, which will be, so the first row is already sorted, so there is no change. The second row will be changed to 1, 3, 9. The third row, which was 1, 8, 5, will be changed to 1, 5, 8. Note that this np.sort always sorts the array in an ascending order. And in case we want to sort an array in descending order, we will be using negative of array as an input, and then we will be negating the result. So let's look at it by an example. So we want to sort this array in descending order along the axis equal to 0, that is along the columns. So we will sort the negative of A, and we will pass the arguments axis the value 0, and then we will negate the result of the returned by the sort function. So this will result in an array sorted in a descending order. So now this is the result where the columns have been sorted in a descending order. So initially it was 4, 9, 1, and now it has changed to 941. The next function we are looking is argsort, which return the indexes of the elements such that if we arranges the elements according to the returned indexes, the array will be sorted. So np.argsort, when x is equal to none, will first convert this array into one-dimensional array, and then will return the indexes of the elements such that rearranging the elements along according to the returned indexes will result in a sorted array. So this is the argsort output when the x is value is none, which means the fifth element should come first. And if we look here in this array A, the fifth element is 1. Remember, in array, the indexing starts with 0. So the 0th element is 4, and the first element is 6, and therefore the fifth element will be 1. Then it returns the next index as 6, which is again 1. The next index is 4, which is 3, and so on. So this will finally result into this array if we rearranges the elements of this array according to these indexes. Now we can also do this argsort along a particular axis. So if we do it along x is equal to 0, it will return the indexes along the columns, and if we do x is equal to 1, it will return the indexes of the elements along the rows, so that the such that the elements rearranged according to these indexes will result in a sorted row. The next operation is concatenation. We use the function np.concatenate to concatenate two arrays. So these is being passed as a tuple here, and we also need to mention the axis along which we want to add them. So if axis is null, then again the 2D array will be converted to 1D array, and then these two 1D arrays will be joined together to give a larger 1D array. So when axis was none, the first array A, so we have these two arrays A and B, right? So the array A was flattened, and this is the elements of the array A. The second array is B, which is the same as we have been using in the previous experiments, and these elements here will now be added to this array. So this will be the array B. If we use the concatenation along x is equal to 0, then it means the columns of A will now be followed by the columns of B. So this is the array A, and this is the array B, and after concatenation along x is equal to 0, it looks like this. That is, the columns of array A are now being extended by the columns of array B. If we do x is equal to 1, then the rows of array A will be extended by the rows of array B. So this is the row of array A. This was the row of array B. And after concatenation, these two have been merged to give the single row of the array. The other way of concatenating arrays is using horizontal stack and vertical stack. So if we pass these two arrays A and B to this function np.hstack, it will result in the horizontal stacking of the arrays. So by horizontal stacking, we means that the concatenation will be happening along the rows. Similarly, for the vertical stacking, it means the concatenation will be happening along the columns. So this is similar to concatenating with x is equal to 0, and horizontal stacking is similar to concatenation with x is equal to 1. So this is how we can merge multiple arrays into one in NumPy. The next is, how can we reshape an array? So to reshape an array, we first need to know its size and dimensions, which we can easily find using this attribute ndarray.ndime, which will return the number of dimensions of the array, ndarray.shape, which will return the shape of this n-dimensional array as a tuple with n elements, and each such that the ith element of the tuple will be the length of the ith dimension of the array. And this ND_array.size will return the total number of elements present in an array. That is multiplying each element of this tuple. ND_array.reshape will help in reshaping the array to the new shape. We can also convert any array to one-dimensional array using np.flatten and np.label. Or we can add new dimensions to the array using these np.newAxis and np.newExpand dimensions. Expand times. So here we'll look at it by an example. A is a NumPy array defined similar to what we have been using so far. So if we print the number of dimensions, we will call a.n_time and to return the number of dimensions to be 2. To print the shape of the array, we will call a.shape and will result the shape as a tuple. So this has been returned as a tuple 3, 3, which means there are 3 rows and 3 columns. Then the size of the array has been printed using a.size, which will return the number of elements present in an array. Now let's try to reshape this array into a new shape, which is 1, 9, which means there will be one row having 9 elements. So we will just call this A is the array which we want to reshape. So a.reshape and passing the new shape parameters, which is 1, 9. And this will result in a new array with the shape 4, 6, 8, 9, 3, 1, 1, 8, 5. Now, if you want to add new axis to the array, we can do so by using the np.newAxis or np.expand times. So let's first try adding a new axis along the 0 dimension using np.newAxis. So B is now a new array. B is an array which is having one more dimension than A. So it is A of np.newAxis, colon. So now the shape will be 1, 3, 3. So remember the shape of the array was 3, 3. And we have expanded the axis, a new dimension along axis equal to 0. So it will happen just before the axis 0 and the new shape will be 1, 3, 3. Similarly, we can get the similar output using np.expand times of the array A along axis equal to 0. And this will again give you the same array reshaped with the same size 1, 3, 3. The other way can be just simply using the reshape function by just passing the new shape, which will be whatever was the shape of the array, just append 1 at the beginning of it. So this will be the new shape of this array. So this is how we can add new dimensions to the array. Indexing and slicing. Indexing means if you want to process any element of the array, we need to index it, right? So indexing basically, NumPy allows indexing array using tuple of non-negative integers, booleans, arrays, or integers. And slicing is like retrieving a sub-array from a big array. So NumPy allows different ways to do it. So let's look at them one by one. A is a simple 2D NumPy array defined here. This time we have added certain 0 elements to it. So if we print A of 1, so it means the first element of this array, 2D array, so it will be the second row. So this is the 0th element of the 2D array, this is the first element of the array, and this is the second element, right? So the first element is nothing but the second row, so it has been written here as 0, 3, 0, 3, 1. We can also return a specific element and not the entire row by using a tuple of 1, 1 because it's a 2D array. So it will return the second element of the second row, which is 3. It has been printed here. The third is we can, instead of printing one specific element, we might want to print certain consecutive elements, which can be done again using multiple arguments, multiple values, 1 per dimension. So let's say 0 here means I am talking about the 0th row. And for the 0th row, I want 0 and 1 like that is the first two elements of this row. So it will return 4 and 6. So this is indexing by an integer, indexing by a tuple, indexing using range. We can also retrieve certain values in an array which satisfy a particular condition. So what if I want all those elements in an array A which are greater than 4? So for that, I can call something like this. A of A greater than 4 will result in all the elements in an array which are greater than 4. So 6, 8, 5. We can also use multiple conditions. So I want the elements to be greater than 4 and also divisible by 2. In that case, you will use a logical operator AND. So this is one condition. A should be greater than 4. The second condition is the elements should be divisible by 2, and we want both the conditions to be satisfied. So we have used here a logical AND. And now doing this will return only those elements which are greater than 4 and divisible by 2. We can also index by arrays. So np.nonzero is a function which returns the position of all those elements which are not 0 in an array A. So for this array A, if we do np.nonzero and print P, B will be a tuple of two arrays. The first array is storing the row indexes, and the second array is storing the column indexes of the corresponding non-zero elements present in an array. Now to print the non-zero elements in an array, we can simply do A of P, and it will print all the elements in an array which are not 0. So this is an example of indexing by arrays in NumPy. The last topic we will be covering in NumPy is copying arrays. For this, we use the function np.copy, which creates a new array object with a copy of the data. And whatever the changes we will make in the copied array, it will not be reflected in the original data. So let's look at it. Here A is a NumPy array again, and B has been created by calling function copy on the array A. So now we store the same data as A, and we do an increment operation on B. So B equal to B plus 1 will mean that each element of B should be incremented by 1. And after performing this arithmetic operation, let's try to print the values of A and B. So when we print the values of A, it remains unchanged, similar to what it was before doing any operation on array B. And the content of the B has, however, changed. They have incremented by 1. So now 4 has become 5, 6 has become 7, and so on. So with this, we come to the end of the tutorial on NumPy.